Hey, what's up, guys? This is Chung here. So this time, LeetCode number 1986. Minimum number of work sessions to finish the tasks. Okay. So this time we have n tasks assigned to us, and we have a list, right, of the tasks that where the i's tasks take this hours to finish, right? And then we have a work session, right? So the work session is when you work for at most session time consecutive hours and then take a break. Okay. And then you should finish the given task in a way that satisfies the following conditions. Okay, so if you start a task in a work session, you must complete it in the same work session. Okay, and this you can start a new task immediately after finishing the previous one. Okay, and then you may complete the task in any order. Okay, and then we need to return the minimum number of work sessions, right, needed to finish all the tasks following the conditions above. Okay. So basically, what does this mean? It means that we have a session time, right? We can put any task in this session as long as the total hours don't exceed the session time, right? And we can pick the task in any order, and we just need to find the minimum session we need to finish the task, right? So for example, we have 3 tasks, 1, 2, and 3. The session time is 3. So obviously, the answer will be 2 because we can put 1 and 2 into one session and then 3 into another session. In that way, we only need two sessions to finish all the tasks. Right, here's another one. Okay, and yeah, so the constraint is like n is on 14, and the session is basically it's guaranteed, right, to be greater than the maximum tasks, so that we can be sure we can finish all the tasks, right? Mm, yeah, so this one is like a very typical I would say Bitmask DP problem, right? So whenever you see like this n range within like only under 20, you can almost be certain you should use something like all possible subset. It's going to be a 2 to the power of n, which is going to be lead to a Bitmask, right? So basically, we're going to use the Bitmask to represent the current state for each of the tasks, right? So at the beginning, everything is 0. 0 means that it has not been finished yet. So, right, and then we're gonna loop through each of the tasks, right, and to see, okay, if we can put this task into the current session, right? If it is, and then we just mark this one from 0 to 1, and then I'll also update the remaining time, and then we'll move forward, right? So which means besides this bit mask, we also need like another uh, state called remain time, maybe, right? And then we just need to get the minimum out of all the possible combinations, right? So the idea is pretty simple, but we're gonna try to code the naive DP approach, and then we're gonna try to improve that a little bit, right? So so DP we have two state, right? First one is the mask, right? And then the second one is this remain time, right? So this DP means that given the current mask, the current state, and the remain time, what's gonna be the minimum sessions we need, right, to finish this remaining tasks and with this remaining time, right? And so for this kind of problem, I always find the top down is a little bit it's more like straightforward, right? More intuitive. So let's do it then. So like we have mask, right, and then we have remain time, right? So we have these two with this memorization. Okay. So what's going to be the end state, right? Basically, if the mask is equal to, okay, we need n here. So n is going to be the tasks. Yeah. So whenever the mask is equal to this O1 state, right? Then we return 0. Oh, right? So this is like how we get. So let's say, for example, n is equal to 3, right? So what we need? We need that. So whenever the state is 1, 1, 1, then that's when we stop, right? So that's how we get this 1, 1, 1. Okay, and we have an answer. It's going to be the system dot max size. Okay. So then we loop through each tasks, right? For I in range of n, right? And we check if this one it has not, if this current bit value is 0, right? So how can we do that? We do a mask, we do a bitwise AND with this one. If this one is equal to 0, right? And then we know this bit value is 0, right? This is a little bit bit manipulation, right? And then we check if the task, if the current task is either can be fit in the remaining session, right? Then we just need to update the remaining session, right? Which is going to be the DP of in the mask. So we update the mask to be to this value to 1. So that's how we do XOR this, right? So that's how we update this bit value from 0 to 1, right? And then okay, and then the remaining value is going to be remain time minus tasks I, right? So that's how we update that. Else means if the current one cannot be fit into the remain time, it means that we need to start a new session, right? Which means we're gonna do a +1, right? So I'm gonna copy and paste. It's gonna be 1 plus this one, right? So we still need to mark this one to be 1, but this time it's gonna be a session minus task, right? Since we're starting with a new session, right? And then after putting the first task into the new session, that this is our remaining time. Okay, and then return the answer, right? So we do a DP 0 and 0, right? So here, the remain time should be 0, right? Because it means that at the beginning we need 1 session, right, to start with. If we put like a session time, then it will be one. The answer will be 1 less, right? Okay, so that's it, right? Pretty straightforward. Oh, let me. This should work. Let me run the code here. Okay, if I submit. Mm. Yeah. Oh my God. So this one even it passed even with this over 10 seconds. Oh, huh. This is not something you will see I mean each day, right? Usually when it exceeds 10 seconds, it will TLE, but for some reason this one even passed. Okay, so and yeah, as you guys can see, this one is pretty slow. So the time complexity, because we have 2 state, right? So like I said, we have this mask is 2 to the power of n, right? And the remain time is like what? So we have a n, right? And then let's say the session time is m. That's why we have a 2 to the power of n times m, right? So that's the total number of the state, and then within each state we have a for loop of length n. So that's the total time complexity, and that's why this one is pretty slow, right? So what we can do to improve that, so we can remove this remain time. Okay, so we can remove this remain time. Basically, we can reduce the time complexity by removing this m from this this value. And how are we going to do it? So in order to do it, we have to understand the nature of this DP, right? So what are we doing here? So basically, we're trying to improve our answer, right? So whenever we have a better answer from another branch, we'll use that better answer to update the current answer, right? So if we were to remove this remain time, what does it mean? It means that we need to somehow return this remain time from this DP, because we need this remain time regardless, because we need this one to determine if we need to create a new session or not, right? So let's say we remove this remain time, okay, and then let's say we are returning this remain time from here, okay. So so here I guess it's going to be 0 and 0. It means that the if everything is assigned, then we don't need to worry about remaining time anymore, right? And here, okay, so here we can just start with the remain time equal to 0. So the reason we are setting this answer equals to this one is because we want to start with the worst of this answer. The worst of this answer is basically is the maximum number possible, right? And the way we're improving it, we're trying to get a smaller number from this answer. Same thing for this remain time. Okay, so the worst of the remain time is what? It's 0, right? It means that we don't have any remain time left. We don't have any remain time left. So, and what's going to be a better result for the remain time? Of course, it's going to be the bigger the better, right? It means that we can get more remain time for the future tasks, right? So that's why same thing here. We're gonna comment out this part, right? So let's see, what do we have? We have answer 1 and remain time 1, right? Return from this mask of this I, right? So let's say we have a DP, as we have already redefined the DP to return 2 values. It's going to be answer 1 and remain time 1. Okay. So now we have 2 values returned. So what are we gonna do here? So we're gonna do the similar check, right? So basically, if the task, right, if the task I can be fit in this remain time returned from the DP, we're gonna update the remain time, right? Remain time 1 equals to tasks I. Okay, right? Because with this remain time, and we need to we basically here we're saying that, okay, so we can put this task within this remain time, which means we don't need to start a new session, right? Else what? Also means we need to start a new session. Means that basically this, okay, so this is the answer 1, means that that's the best we can do, right, with this state, which means the best we can do with this state is having this new session while we can have this kind of remain time, right, to finish the remaining tasks, right? So like I said, if the current one cannot be fit into this to the remaining time, it means that we need a new session. It means that we need to increase this answer by 1, right? And then the remain time 1 will become to what? Similar like this one. It's going to become to this one, right? Session time minus task I, right? And then here we check if the answer or the remain time can be improved, right? So that's the nature of the DP here. So first, how do we check that? So first, if the answer 1 is smaller than answer, so this is definitely a way, an improvement, because the session is smaller. The number of session is smaller than the current answer, right? Then another for loop, another branch. That's when we will definitely update the answer. Or what? Or the remain time is improved. That's another improvement, because if the answer is the same, if the answer doesn't change, but the remain time but the remain time 1 is greater than the remain time, right? So this is another improvement. It means that even though the answer, the number of sessions didn't change, right? But the remain time becomes bigger. it means that this is another improvement, right? It means that we have more time for the other tasks. That's when we will also update. That's when we need to update both, right? It's going to be answer 1, and then remain time equals to remain time 1, right? So here we return both remain time. Okay, and here it's going to be a 0, right? In the end, we just need to return the first one from this. Okay, so let's run it again. Right, see, this one is much faster, right? Because we removed a number of states, right? Yeah, I think that's it, right? I mean, so for this one, the first one is the first approach is pretty straightforward. It's a very standard of DP of two-state DP plus a little bit of bit manipulation, right? But the second one is a little bit tricky to come up with, right? Basically, we're trying to remove the second uh, state, but keep in mind, not every time you can remove the one state from DP. It's just for this problem, we can, because the second state is related to the first one, right? And we can improve both of them, right? So we return both of them, and then we are trying to improve either of them. As long as either of them can be improved, right? That's when we will update the answer, right? And I think this is something new to me as well. So better keep that in mind. Cool. I think that's it, and I'll stop here. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.